Final chapter here. So, here in chapter 15, we're talking about sort of equilibrium. And last time we got into a little bit about sort of the rate of reaction, again, how reactions sort of take. Again, a reminder that you basically need kind of two things to occur when a reaction takes place. You really need some type of collision, and you need the right amount of energy. And remember that when we do a chemical reaction, the only thing that's happening is we're breaking bonds, and as they go from reactants to products, all the bonds are breaking, and then we're basically remaking new bonds on the product side. And that's again how we get sort of our uh, conservation of the elements. Because it only involves electrons, nothing involving the neutrons in a chemical reaction. We never change any elements that are involved. So we talked about sort of the energy diagram that we've seen before in previous chapter 10, I think. And remember that we can have a situation such as this. And we have our reactants to our products. And remember that in this particular case, our reactants are higher in energy than our products. And that means overall energy is going to be released here. And this is going to be an exothermic diagram. And what happens is as these reactants start colliding and collisions occurring, they start to break these bonds as they climb this hill of energy to sort of get to the other side. And they're also starting to sort of make bonds as well as they're sort of climbing this hill. And that hill does have a specific sort of name, and that is again, the activation energy hill, which is sometimes abbreviated E of A. And that is the minimum amount of energy that's required really for a reaction to take place. So that is again sort of the energy component or barrier that really the reactants has to climb to sort of get to the other side. Remember at the very top of the hill, probably the highest point in energy along the way. This is again sometimes referred to as the transition state. And at the transition state, we really usually will have some type of transition state complex, which is a really high energy, oftentimes unstable because it's very high in energy, sort of substance that has partially broken bonds, also partially made bonds at the same time. That's also why it's very high in energy. It's a sort of unstable sort of situation. And what happens is very quickly, they'll usually kind of drop down to the other side and form product. And that's what it's sort of an exothermic diagram looks like. Again, an endothermic diagram is similar. The main difference, though, is actually the location of your reactants versus your product. Here, the reactants are lower in energy than the products. So, in order for energy or the reactants to sort of get up there, products, this is an endothermic process where energy has to be absorbed to do so. Again, same idea in this one. We're still going to get some breaking of bonds, making of bonds as we sort of chug up the hill there. We do see in this particular case here a little bigger activation energy. And again, we also have our transition state up there. And again, we'll kind of break down to the bottom side. Now, this sort of hill of energy that reactants have to climb to the other side has a big effect on the rate of reaction, how fast or slow that reaction will take place. Obviously, the bigger sort of energy barrier there is between the reactants and the products, probably the slower that reaction is going to be in comparison to a reaction where you have a smaller activation energy, a smaller hill to get to the other side. With a smaller hill to the other side, typically, what that also means is you'll have a lot more reactants that have enough energy to actually be able to get to the side versus one with a big yield. You may not have as many reactants that can kind of get up and reach the other side. So it does play a sort of direct role in terms of how fast or slow a reaction may take place. Remember another sort of thing that we talked about in that earlier chapter 10, when we talked about energy, which was known as the enthalpy of a reaction, which is the change in enthalpy. And that is really just like the heat of a reaction. Overall, is the reaction going to sort of gain energy? Overall, is the reaction going to sort of release energy? The way that we can calculate delta H, as we talked about, is you can basically take all the delta H's of your products and you minus it from all the delta H's of your reactants. If you remember, we talked about sort of state functions, and the idea of what really is important is sort of where you started and where you ended up. It doesn't really matter how you got there. I think we saw a picture, a couple of guys hiking up a hill, and one cut the direct route, one went around the mountain. The important part in terms of something like that in that picture, which was potential energy, is beginning and ending location. And in a chemical reaction, we can think of sort of initial and final as really our reaction of product. Really, our products obviously is kind of like our final state. Our initial state is really our reactants. So that's why in a lot of these sort of values, we take all the energy of our products minus the energy of our reactants to sort of give us where we ended to where we began. Now, when we look at a diagram such as this, the delta H is calculated really by the difference between the energy of the products versus the reactants. And if you remember, when we have a delta H that is negative, that is an exothermic process. And the reason for that, if you just look at the graph here, when we calculate delta H by taking our products minus our reactants, in this case, our products is a lower number or smaller number in terms of energy than our reactants. That's a larger number. So typically, if you take a smaller number minus a larger number, you're going to end up with a negative number in this case. And that, again, is why delta H is negative for an exothermic reaction. As opposed to over here, when we look at the difference between the reactants and the products, that is the delta H of the reaction. And once again here, if we kind of do the same sort of calculation, the delta H of the reactants, our reaction, is our products minus our reactants. And in this case, our reactants are actually higher, are lower in energy than our products. So we actually will have a larger number minus a smaller number. And that usually will result in a positive value for delta H. And delta H typically is positive in an endothermic situation for that specific reason there. Any questions on some of that stuff there we talked about last time? All right, so continuing on here, still looking a little bit at the energy diagram, I think. There it is. One of the ways, though, that we can speed up a reaction, and we talked about it, I think, a few times throughout the semester here, is by basically adding a catalyst. And a catalyst is not a reactant. Again, not really a reactant. It is not a product. And basically in the reaction, it does not get used up. So the idea of a catalyst is really there to find a more efficient pathway for this reaction to take place than it would if it was not present. That's essentially how most catalysts work. And catalysts can be something as simple, again, as like a metal. And for example, if you had maybe a reaction where you had gas molecules kind of flying around, and outside of a catalyst being present, you would have to kind of wait for them to kind of come in contact with each other and sort of just hope that they sort of come about each other as they're flying around. Now, if you added something like a catalyst, which could be like some type of metal. Now, what could happen in this situation is these gas molecules, maybe that are flying around, will maybe be attracted towards the metal and the catalyst. And what that essentially will do is now put those gas molecules in a much closer proximity to each other. And that will then allow them to sort of interact with each other a lot easier. And also sometimes it can help in sort of breaking of bonds and kind of helping the whole process sort of kick off. So you can think of a catalyst as something that is typically added to speed up a chemical reaction. There are actually catalysts that will slow down a reaction, but most of the time when people talk about a catalyst, they're usually talking about it in the aspect of it speeding up a chemical reaction. Those are sometimes referred to as positive catalysts. Negative catalysts typically will slow down a reaction, but most of the time people are talking about it in terms of speeding up the reaction. By finding this sort of alternative pathway, this more efficient pathway, what it does, look at the energy diagram here, is this is the uncatalyzed reaction, and that is the hill in the uncatalyzed reaction. Everybody has to climb to get to their side. But by finding this more efficient way, what it essentially is able to do is lower the activation energy hill. And by lowering the activation energy hill, now instead of having to go up that purple hill, the reactants just need to go up this smaller blue hill basically to get to the other side. What that's ultimately going to do is create a bigger pool of reactant molecules that have enough energy to get up and over that smaller hill versus the bigger hill that they would have to normally climb. And ultimately, what that sort of translates to is you now have more reactant molecules to get to the other side, which is going to increase the collisions and increase the sort of suitable collisions to make products, and that's going to ultimately speed up the reaction rate by doing that. So that's ultimately how, again, a catalyst sort of works. It just kind of finds a more efficient pathway for doing so. Ultimately, it kind of lowers the overall energy barrier for the reactants to get to the other side, and thus, by doing so, will speed up the reaction because, again, there's just going to be a greater amount of people our reactants are going to go, I'm going to go over the smaller hill, no problem. I don't think I really want to go over the bigger hill when there's no catalyst present and not going to go to the other side. Any questions on that there? No. All right, so we're then going to really talk about equilibrium here for the rest of the chapter. And equilibrium, as I might have touched upon last time, does involve, again, a specific type of reaction. So when we talk about chemical equilibrium, it involves these reactions which are, again, reversible reactions. And you typically can see these are reversible reactions because they do have arrows that head in both directions. And once again, what that means is you could think of this reaction as kind of like a two-way street. There's kind of like a forward way and a reverse way, as opposed to when you have a reaction that has basically one arrow, you can think of it as like a one-way street direction. They're only going in one direction. Nobody's coming back the other way. So this reaction will have, again, as the reactants go to products, this is what is sometimes referred to as the forward direction. And at some point, when you actually do build up enough products, those products will actually decide, we'll start reacting with each other, and we'll actually go back in the other direction. And at some point, once you build up enough of those products, the products will recombine and actually form back to reactants. And that is what is referred to as the reverse direction of this reaction. So again, this is really a kind of two-way street. There's a forward direction, a reverse direction in these type of reactions. And now the important part here is when it does reach chemical equilibrium, and we might touch upon it earlier, but again, a reminder that when it talks about reaching equilibrium, it does not mean that we have like the same amount of everything on each side of the arrows or anything like that. What it is actually referring to is what we sort of talked about here at the beginning of this chapter, which is the rate of the reaction. And what that has to do is once it reaches chemical equilibrium, the rate of the forward direction, where your reactants are going to products, will eventually equal the rate of the reverse direction, where those products then come back into the other spot. So what does that essentially do to the concentrations of everybody in this reaction, or even the pressures of everybody in this reaction, if we're dealing with gases? What it essentially does is once it reaches equilibrium, it essentially locks everybody into place in terms of their concentrations. So whatever their concentrations might be when it reaches equilibrium, they basically will be locked into place and may be able to maintain those concentrations. So once again, as just a basic example here, if we initially started with, again, 2 molar this guy, 4 molar this guy, and nothing of these guys, when this reaction reaches equilibrium, maybe we got 1 molar this guy, 2 molar this guy, 3 molar this guy, and like maybe 4 molar of this guy. What happens at that point of equilibrium is all these guys will basically maintain these concentrations indefinitely. So they'll just be able to maintain them because the idea here is just as quick as we go this way, it's just going to shoot back the other way just as quick. And because those rates are equal to each other, again, it essentially just locks everybody into place forever, basically, or until you kind of screw up the equilibrium, which you can. And we'll talk a little bit about that here in this chapter, that you can do things to it that will mess up the equilibrium, but ultimately here it will basically lock into place. Now, one of the things that are interesting about these type of reactions is, let's just say you did one of these reactions. Wish they took the lab out of this class so you don't do it anymore, but let's just say you did, and you got this reaction to equilibrium, and let's just say it kind of turned like a reddish color when you mixed everything together. And when you look at, for example, the beaker, you'll go, well, it kind of just turned red. It's over. Nothing much is happening at this point. And it may appear to you that this reaction is over. There's nothing happening. But again, if you were to sort of super zoom in on the liquid and the reaction here, what you would see is you have a lot of activity actually happening. You have a lot of A's and B's going to C's and D's in this example, and you have a lot of C's and D's going back and forth. So there's a lot of activity that's continuing to happen in these type of reactions to, for example, maintain that red color that you're looking at in that beaker. And then sometimes people, again, sort of think in these type of reactions, like, all right, it's like over. I saw this color change. Nothing else is happening. Nobody else is reacting. But they're continuing to react constantly here. So sort of on the big scale, it looks like, once something reaches equilibrium, it's all done. But if you're to sort of zoom in on the microscopic scale, you see a lot of activity continuing to happen. You see a lot of forward reactions happening, reverse reactions happening in these type of situations. Again, to sort of maintain, for example, in this case, the red color. Any questions on that there? So equilibrium is the balancing of two processes in which the opposite of each other sort of happen. A very common place that we see equilibrium reached is when we change phases. And for example, if we take water as an example, at 0 degrees Celsius, which is this normal melting point and freezing point, you have an equilibrium that exists between solid and liquid and solid. So at exactly 0 degrees Celsius, you basically have both phases happening at the same time. They have reached equilibrium with each other. So that's why you have a little bit of solid ice at that point. You got a little bit of liquid water happening at that point, and it maintains that until you get a little bit above 0 degrees in the case of water, or a little below 0 degrees, that you actually get the full sort of transition of one phase versus the other. But exactly at those transitions, we do have basically an equilibrium established. And if you remember when we talked about in the energy chapter, or the last chapter, maybe 14, there is some heat associated with that transition. And that, again, is the delta H of fusion. That's the energy required to make that transition between solid and liquid, or liquid and solid. Same thing happens at the normal boiling point. So if you're talking about something like water at 100 degrees Celsius, which is the normal boiling point of water, we also have equilibrium between liquid and the gas phase, and gas and the liquid phase. And again, at exactly 100 degrees, we got a little bit of everybody there. We got some sort of a gas, and we got some liquid happening. Again, it's not until you get, in the case of water, above 100 or below 100 degrees that you fully transition sort of one way or the other. And that's what we see here. That's evaporation and condensation here. And in a closed container like this, again, we're going to reach equilibrium. And what you'll have is basically at the surface of the liquid in that container, you'll have some gas molecules kind of jumping out. You have some gas molecules jumping back in. Once it reaches equilibrium, it's going to kind of lock into place how much gas molecules you have over the liquid and obviously how many liquid molecules you'll have. Although they're constantly going back and forth, the rate at which they're doing that gives you a net no change in the amount of gas molecules above the liquid or the amount of liquid molecules obviously on the bottom in that case. Even though there is constant movement out and in, out and in, it's happening at the same rate. So it just kind of doesn't get a net change of anything sort of happening overall. And as I mentioned before, it is sort of a dynamic process where, because of that rate of the forward reaction equal in the rate of the reverse reaction, we're just going to lock everybody into place on both sides and really will not change all that much unless you do something to screw it up. And as I mentioned a second ago, um, macroscopically on the big scale, it's very static looking. It looks like nothing much is happening, as my example with the beaker and the red, it turned red. But again, microscopically speaking, there's just a lot of activity that's constantly happening to maintain that equilibrium. The other thing that's interesting in these type of reactions, as we talked about, is these reactions will always, even if you do something to it, like to try to screw up the equilibrium, it will always sort of try to self-correct itself and get itself back to that equilibrium state. So you could kind of play around with these type of reactions a lot. You can let it get to equilibrium. You can then mess up the equilibrium. It will self-correct and get itself back to equilibrium. Again, you can mess it up again and it will self-correct and get itself back to equilibrium. So it's sort of a self-correcting sort of reaction that it adjusts to whatever you do to it that screws up the equilibrium essentially. So it's able to kind of make an adjustment on the fly there to get itself back to equilibrium. And that's sort of what we can kind of see here as well in terms of equilibrium. Initially here you can see we started with really all reactants in this reaction. We had no products. As this reaction starts to take place, the forward direction is predominating because we have no products. So the only direction this reaction can start out is in the forward direction. It has to start to make some products. And that's why we see our reactants concentration start to decrease. We actually see our product concentration start to increase. And at some point, we continue to kind of see that decrease in reactants and increase in products. And eventually, probably around here, we're going to start to see the products heading back this way a little bit. And as this reaction is taking place, you can see we now lock into equilibrium here as everybody's concentration is basically remains the same. And again, it will continue to remain the same once it does that. And that's also something in terms of an equilibrium sort of reaction, which is if you have no products to begin with, so if you have any type of equilibrium reaction, where initially speaking, perhaps it's very common you have no products in terms of concentration, there's only really one choice for how this reaction has to begin. It cannot go any other way but the forward direction. And as it does that, it's going to start to increase the products. And it's not until these products start to sort of increase that now they have the ability to sort of go back in the other direction. So, in a lot of cases in these reactions, if you only start with reactants, the only option to begin with is the forward direction heading towards the products. But as soon as you start making some products or get a good amount of products formed, they can definitely start combining and start the reverse direction to occur in that case. And that's what we see here in this diagram at sort of the beginning of the reaction. We have no products. It's all reactants. And remember that to make our products, we have to start using our reactants. So we start to see a much bigger decline in the rate of the forward direction. And we start to see at some point, once we start building up, we're going to get an increase in the reverse reaction. And this is really where they reach equilibrium, is where the lines flatten out. And that's where, in this particular case, this is the forward direction versus the reverse direction in this case. And you typically can see some plateau parts that usually occurs. Now, concentrations reach levels where the rate of the forward reaction equals the rate of the reverse reaction. And that, once again, is when chemical equilibrium is reached. Again, even though it says equal in the number, it does not mean that you have equal amounts of everything. It's just really talking about the rates of that forward and reverse direction. So if we had a system such as this, and it has reached equilibrium, and we have it in a container, and we decide to add more water in this case to this equilibrium. So we already have this reaction, it started reacting, it's now reached equilibrium, the rate of the forward direction, the rate of the reverse direction equal each other. And now we want to maybe do something to it that's not going to be happy, and we're going to add some more water in this case. So take a moment and think about what might happen to everybody's concentrations if in a container I have this reaction happening. So if I have this reaction happening, what that again means is I got a little bit of everybody already in this container. And now what I want to do is add more water to it. So take a moment. Will these guys' concentrations increase, decrease, or stay the same? The concentrations. So for each of the ones in the reaction, take a moment to try to think about what will actually happen in this case. And we'll talk about it here in a second. Okay, so let's take a look. So in this particular case, I'm going to add more water, which is over here in the reaction. And what that's going to essentially do in this case is it is going to increase the amount of reactants that I have floating around, right? Because I just added more water. And remember, one of the things that helps with the rate of the reaction is the availability of things to collide with each other and start a reaction. So ultimately what's going to happen is because I added more water, which is a reactant, I now have more reactants and products, which is going to allow my reactants really a greater opportunity to find each other and start actually reacting because, there's just a lot more in there. And what that ultimately is going to do is cause the forward direction in this case basically to occur because the reactants are going to have no problem finding each other. That's going to cause our reactants to start to actually react with each other and form products. Now, because of that, we would expect the concentration of CO, should it go up or down in that case? It should go, the concentration of CO in this case actually should go down. And that is because you need both reactants to come together to make your products, right? So they both have to come together to make your products. So we would expect the concentration of CO to go down. On the other hand, now that the forward direction is happening, we would definitely expect more products to be formed in this case. And we would expect the concentration of H2 to go up and the concentration of CO2 to also increase as well. Because again, at this point, that forward direction of this reaction is going to predominate. Now, when we talk about water, what's going to happen with the water? Well, a couple of things going to happen with the water. The first thing that's going to actually happen with the water is it is going to go up, and it's going to go up because you added it, right? So you artificially added it, so it's going to basically go up. But once it starts reacting with the CO in that forward direction, you then should start to see it really come down. So you'll kind of see a jump in it because you artificially added it. But once that forward direction happens and it starts reacting with the CO in this case, you should start to see the concentration come down. What might end up happening is you might actually end up with more than you started with, and that's only because you artificially added it. So even though you jumped it up high, and then it's going to start to drop down, it may actually end higher than it started with in some cases, only because you artificially kind of bumped it up there. But the overall trend that should happen is both H2O and the CO in this case should start to decrease because we're kicking off that forward direction where our reactants are going to our products, and we again should start to see our products starting to increase. Any questions on that there? All right, so if we take a look at the same reaction, maybe not. Let's see, try this again. Try that. All right, now looking at this exact same reaction, but in this case, what we're going to do is add H2 to it. So same idea for each thing that is in this reaction. If you have this guy, once again, in a container where this reaction is taking place, and you added some H2 to it, will we see an increase, decrease, or will our concentrations stay the same? So take a moment there and kind of think about what will happen. Situation, but in this case, we are adding H2. And when we look at the reaction or equation here, H2 is actually a product. So it's kind of the same idea as what we had with the water. In this particular case, though, because we're adding H2, we now will have more products than we do have reactants. And what that's going to happen in this sort of reversible reaction is that is going to cause the availability of our products to be much greater than our reactants. And that's going to cause those products to actually start colliding with each other because, again, there's just a greater concentration of them at this point. And ultimately, what that's going to kick off in this case is actually the reverse reaction is going to kick off in this case. So this is going to kick off the reverse reaction. And because of that, this reaction is going to head to the left. And the only way it can head to the left is the concentration of CO2 in this case will once again has to come down because in this case, we actually need both products to come together to head backwards towards the reactant side. So we need to kind of decrease our products. Because this reverse reaction is going to occur, we will see an increase in our reactants in this case, because again, this reaction is now heading in the left-hand direction. It's kind of going in that way. And in terms of H2, we once again will see a similar probably outcome than we saw with H2O. Again, it will artificially jump higher because you added it. But once it starts reacting with the CO2, we will start to see it come back down. And once again, it again may end up actually higher than it started with, only because you kind of added it and artificially did it. So this is actually a really big principle that happens in these type of reactions, which is you can kind of manipulate these reactions. And this is one way that you could kind of manipulate these reactions. Let's just say that I wanted more reactants than products. I could do something like this and add some H2, and that will cause the equilibrium to shift to the left, and I'll end up with a lot more reactants being made. Or maybe I wanted more products, like the first example. I could add something like water to this equilibrium. I could cause the reaction to shift to the right and get more products. So these are very sort of flexible reactions in that case. You can do a lot of things to them to sort of exploit the idea that there is these two directions that occur, and it will want to get itself back to equilibrium sort of state. And like I said, in some cases, you may be doing a reaction where you just really want almost all products to be formed. And you can start with a lot of one of the reactants, and that will definitely force the reaction all the way to the right. Any questions on that there? What button? There it is. Now, another relationship that occurs in an equilibrium reaction is what is known as the equilibrium constant. And the equilibrium constant is abbreviated with a big K. And I say capital K because a small k is actually what's known as the rate constant, so it's something different. So capital K here is the equilibrium constant, and it is a constant value for a reaction the way it is written and at a specific temperature. So this is a constant value. Ultimately, the way that we calculate the equilibrium constant is you take all the concentrations of your products and you divide it by all the concentrations of your reactants. So once it reaches equilibrium, you take all the concentration of your products divided by all the concentration of your reactants. And one of the nice things about equilibrium is it is actually just a number. There are actually no units associated with it. We actually have seen an equilibrium constant value. We actually saw one in the last chapter. Do you remember our friend Kw? That is an equilibrium constant. And it is an equilibrium constant for water, which sets up an equilibrium between H plus and OH minus. And that is basically what Kw is. As you can see, products over reactants. And in this particular case, one of the two things that are not included in this expression, as we'll talk about, is anything that is a solid or a liquid is not included when you write the expression. That basically gives you really only two things that are included. It is anything that has an aqueous symbol next to it or anything that is a gas. They are included. Now, the reason why, for example, solids and liquids are typically not included in the equilibrium expression is because they really don't participate in the equilibrium. Solids, if you think about it, are just kind of sitting there. They're not really doing much. They're just kind of like a rock on the bottom of a jar of water. They're not really participating all that much. Liquids, on the other hand, their concentrations are usually so high that they don't change all that much in the reaction, and they remain relatively constant. And that is why if you look at this Kw that we saw earlier in the previous chapter, we took our products and our reactants is actually a liquid. And that is why it's not included in the equilibrium constant that we saw earlier. In this case, it is just the products. Now, another really important thing with that is when we do products over reactants, we do have to take the coefficients as the exponents when we do that. So the coefficients in the balance equation become the exponents here. This type of equilibrium constant, and there's a lot of different types of equilibrium constants. If you take Chem 1B, pretty much that class is brought to you by the letter K. You'll learn every single equilibrium constant you never wanted to know about. Kw, Ka, Kb, Kc, Kp, Ksp, Kf. There's a ton of them. And but they all are basically the same thing. They're all basically the ratio of the products to the reactants. And in this particular case, a reminder that when we do see brackets like this, it does mean concentration. And usually what that means, again, is molarity. So usually when we see those brackets, we're talking about the molarity here. And sometimes you will see a little symbol on the bottom of the K. And for example, this one would most likely be Kc. And C means that you did this for concentration, basically. So you did the equilibrium constant for concentrations of everybody. And again, we would take the concentration of our products over the concentration of our reactants. Now, for example, if everybody in this reaction were all gases, for example, if these were all gases in this reaction, you could also write a similar equilibrium constant just to kind of show you the difference. You could also do the same thing, but you could write one that involves pressure, because as we know, when we deal with gases, pressure is a very big property. And you could do the same thing. You could do the partial pressure of C to the C, partial pressure of D to the D, divided by our reactants, partial pressure of A to the A, and partial pressure of B to the B in this case. And since all these would be done in pressure units, like atmospheres is probably the units you would use, this is sometimes referred to as the Kp value, P meaning pressure. Ka, as you'll learn in 1B, means you did it with an acid. Kb means you did it with a base. Ksp means you did it for something that's insoluble. Kf means you did it for a complex ion. So they're all sort of really the same thing. There's just sort of different applications of it. When you do have an equilibrium expression like this, in order to calculate it, you do need the equilibrium concentrations. So these have to be equilibrium concentrations to go into this expression and actually get a number. Any questions on that there? Now, what does this number really tell us? Since it's just a number, go here. So if it's just a number, when we calculate k and it equals a number, there's really two options for what you can end up with. You could end up with a large value of k, or you could really end up with a small value of k. And once again, k is basically your products over your reactants. So for example, if I had a large value of k, what that essentially means is when this reaction reaches equilibrium, should I expect to have perhaps more reactants or products if I end up with a large number for it? So in terms of this, just mathematically speaking, if I take a large number divided by a small number, what type of number do I end up with? You never end up with a large number. So if you have a large value of k, what essentially that means is when you reach equilibrium, you would expect to have more products than reactants. And again, the ratio of products to reactants will be more, and that's going to give you a large value of k. So when that thing reaches equilibrium, you would mainly expect to have more products. And same idea, if you had a small value of k, that would mean the only way mathematically speaking you could get a small value is you would need more reactants than products. So you would need a larger number here and a smaller number here. If you take a small number divided by a large number, you end up with a small number, and that will get you a small number of k, or value of k. And that means that when you reach equilibrium, you would expect mostly reactants to be involved. So the actual value of k that you end up with is something that will give you an indication of when you reach equilibrium, what you expect to have in terms of concentrations. Now, by no means is this sort of perfect. There is great extremes to this. There are like really large values, and there's like really small values, and there's kind of values in between. And, you know, if you have like a really large value of k, then you would almost expect the reaction to be kind of like a one-way street. And you'd maybe expect to have all products. Just like if you had a really, really small value, extremely small value of k, you expect mainly reactants, not very much products to be there. But one thing that you should remember is even in sort of the extreme conditions of a really large value of k or a really small value of k, it is still a reversible reaction, which means you will always have a little bit of everybody. So if you had a really large value of k, even though this reaction is mainly going towards the product side, there is still a little bit of it that is coming back the other way. So it is still always this reversible reaction, even though you could kind of almost make it go one way or the other, or it may favor one direction a lot more than the other, but there is always a constant kind of two-way street that's occurring in this situation. So what is considered large? What is considered sort of a small value of k? Well, a large value of k is the big number of 1 and above. Yeah. So basically anything above 1 is considered a large value of k. Anything less than 1 is considered a small value of k. Any questions on that? Now, another thing that, in terms of the equilibrium constants, that sometimes confuses people is this. It is a constant value for that reaction, the way it's written, and at that specific temperature. And it will always end up with the same number as long as the temperature stays the same. And what I mean by that is if you took this reaction, for example, this is sort of generic reaction here, and let's just say you did one experiment here where you started with only reactants and you let it come to equilibrium. And then maybe you did another experiment where you started with only products and you let it go to equilibrium. And then maybe you did a third experiment where you started with a little bit of everybody and you let it go to equilibrium. If you did these experiments and you calculated the K value, and this was all done at 25 degrees Celsius, all these experiments, for example, you would get the same K value every single time. And sometimes people go, how could you get the same K value if you like started with all reactants in the first one, or you started with all products, or you started with a little bit of everybody, or maybe in the fourth reaction you doubled the amount of reactants you started with. You're like, shouldn't I end up with different numbers? And the answer is the ratio is really what the equilibrium constant expression is the ratio of products to reactants. And there are many different ways and ratios that will give you the same number. So it's a very simple explanation of that is this. Let's just say our equilibrium constant for this reaction was going to be 2 for those 3 experiments. And if I wanted my equilibrium reaction to be 2, I could definitely, for example, if I did my products over reactants, take 4 divided by 2, that would definitely equal 2. If I did my calculation of products over reactants and I did 2 divided by 1, that would also equal 2. If I did my equilibrium sort of expression and we're calculating my equilibrium constant and I ended up with 16 divided by 8, that would also be 2. So in each of these examples, the sort of fraction, if you will, have different numbers, right? But the ratio of products to reactants all remain the same. And that's how come in these sort of reactions, it really doesn't matter what you start with. You will always end up with the same ratio of products to reactants, and you'll end up with the same equilibrium constant. The absolute only thing that can affect the value of the equilibrium constant is if you change the temperature. So if you change the temperature, you will get a different ratio of products to reactants. So for example, if I did all those 3 experiments a second ago, 1 through 3 at 25 degrees, I would end up, for example, with a K value of 2 for everybody. But let's just say I did those exact same experiments and I did it at 45 degrees Celsius. I would end up maybe with an equilibrium constant of 4 when I did it at 45 degrees versus at 25 degrees. But if I did all 3 of those experiments, I would also end up with the same equilibrium constant for all 3 of those reactions. What we want 2 or 4 there, right? So we want 12 divided by 3. Let's write out 4. So at 45 degrees, every single time I would do the equilibrium constant calculation, I will end up with the same number. At 25 degrees, every time I would do it, I will end up in the same number. But when you compare the value of the equilibrium constant at 25 degrees and 45 degrees, they will actually be different numbers. And that's what we're talking about here is if you change the temperature for that exact same reaction, you will get a different ratio of products to reactants because either the reaction will occur faster or slower in one direction as the temperature changes, and it will come to equilibrium with a different sort of ratio than it would at, say, the lower temperature. Any questions on that? So that's a really important concept to keep in mind about equilibrium reactions. Again, you always end up with that same sort of ratio. So if we take a look at one here and we wanted to write the equilibrium expression for this, once again, we're going to do our products over our reactants. So in this case, it would be the concentration of NH3. The coefficient here is 2. So we will have to square it because of the coefficient. We will then go to our reactants. We have the concentration of N2 Once again, the coefficient here is 1, so much like most of the time in chemistry, you don't really have to put a number there. It's assumed to be 1, but the 1 is kind of there. Times our concentration of our other reactant, which is H2, and again here we have a 3, so once again we will have to cube it. And this again would be done all in concentrations, so this would be what is known really as the Kc value. And again, that's the equilibrium constant done for concentration. This particular reaction, as I mentioned earlier, actually are all gases. So once again, you could write a similar equilibrium, which is known as Kp, which does pressures instead of concentrations. Works the exact same way. This would be the partial pressure squared because of the coefficients of NH3 divided by the partial pressure, again, coefficient is 1 of NH2, and the partial pressure of this guy cubed to the H2. By the way, usually the unit that you would want to use if you're actually calculating something like a Kp value is atmospheres. So atmospheres is kind of the standard unit that you would use in equilibrium situations whenever you're dealing with pressure. Questions on that there? Now, as I mentioned before, K has the same value at a given temperature, regardless of what you start with. So, as I was just explaining a second ago, it doesn't really matter if you start again with all reactants, all products, a little bit of everybody. They will always come to rest as long as the temperature stays the same in each of those situations to the same ratio of products to reactants. And again, that's going to give you your same equilibrium constant value. All right. So here we want to write our equilibrium expression. Once again, we're going to do our products over our reactants. And here, these are all aqueous, so they do get included. So this is going to be, again, the concentration of H plus times the concentration of acetate divided by our reactants. And in this case, it's aqueous, so we will include it. And that gives us our acetic acid on this side here. And again, that would be our Kc value, our K value. Now, you may be asking, can I write a Kp for this particular reaction? And the answer is no, you cannot, because there's no gas. So in order to write a Kp that involves pressure, involves gases, in your reaction, you need to have gases. So here, these are all aqueous, no gases involved. You could really only kind of do a Kc value in this case, or an equilibrium constant involving concentrations. Any questions on that one there? All right. Now, as I mentioned before, you can also calculate the equilibrium constant. And in order to calculate the equilibrium constant, you do need equilibrium concentrations. Or again, if you happen to be doing something with pressures, you would need the equilibrium pressures. Now, if we were given the equilibrium concentrations like we are here, and we wanted to calculate the actual value of the equilibrium constant, we would want to start with our expression. So we would come to our equation, we would take our products, which is NO2. Once again, we're going to square it because of the coefficient. We're going to divide it by our reactant, which is N2O4. And now these are all equilibrium concentrations. So since we have the equilibrium concentrations given to us, we basically just need to plug it in there. So our NO2 was 0.060, and that's going to be squared, divided by our N2O4, 0.055. So again, in this situation, this box there, let's just make sure it's right, hopefully. 0.06 squared divided by 0.055, going to get us a 0.065 as our equilibrium constant. So once again, there are no units associated with it. It is, again, just a number. And now, would we consider this a large value or a small value? Okay. going to be a small value K, which means when we reach equilibrium, again, we would mainly expect to have reactants. In this case, it's not a super, super small value. And again, it's not that big of a difference in this case. All right, let's take a look here. All right. So for each of these here, again, we have what is known as a homogeneous equilibrium. And in a homogeneous equilibrium, much like in a homogeneous mixture where everything's the same throughout, what homogeneous equilibrium means, everybody's in the same phase. So all these guys are in the same phase. And again, if we were to write our equilibrium expressions, our K would be in this case our NH3, and again, squaring it, divided by our N2 and our H2 cubed. In this case, we would take our H plus concentration, our Cn minus concentration, which is our products, divided by our reactants, in this case, our HCN here. Now, there's also heterogeneous equilibrium, which, much like a heterogeneous mixture, means that you do see different phases happening. They're not the same throughout. So you got mixtures of maybe solids, gases, aqueous stuff, all kind of mixed in there. And as I mentioned before, the two things that really are not included in these expressions are, again, anything that is a solid or a liquid. They're really not going to participate in the equilibrium. So we do leave them off the expression. So here for our first one, really the only thing that would be included in this expression is this guy. Everybody else there are solids, so they would be excluded from the expression. And we still do products over reactants. So in this particular case, our equilibrium constant expression is just going to be our product. So this is going to be O2 cubed. And again, we would not include anybody else there because, again, everybody is a solid and they're not included. On the bottom one here, once again, it is actually going to be only the product side in this case that is going to be included. Again, this will not be included. And that would get us our K is equal to our H2 squared because of the coefficient, and our O2 here. Again, no reactants in this case. It is sometimes possible that you could end up with a reaction where only the reactants would actually maybe be involved. So for example, if you had, say, something like this, let's do that. A, the aqueous goes to, just do B to the solid, for example. Now, in this particular case, it's just really the reactants that are involved, not the products. And the way that we would do that is, because this is really not involved, we would actually just do 1 over the reactants in this case, and it would be A squared. So by some chance you come across a weird equation where everything on the product side is either maybe a solid or a liquid, you would not include it, but you need to include somebody on the reactant side. You basically just go 1 over the reactants is sort of how you would write the expression. Any questions on that there? And again, here another example. Here, basically got all solid except for, once again, our products. So we will just include our gases. So gases and aqueous stuff are included. And if you think about it, aqueous basically a lot of times are solutions. And a lot of times those are ions, which are floating around in the solution. They're good to go. They're going to be participating. Gas molecules are basically flying around, right? So they're constantly moving, constantly able to kind of participate in the equilibrium. Again, things like solids are just going to kind of be sitting there not doing much. And like I said earlier, things that are liquids or pure liquids typically have a pretty big concentration that they really don't change all that much from reactants to products, their concentrations, so they remain relatively constant. All right, so for this particular one here, Again, looking at it, if we write our equilibrium expression, products, which is our calcium, times our fluoride, and once again, because of the 2, we do need to square it. Here it is a solid, so it will not be included, and that gives us basically our equilibrium expression, which in this case is just the product side, no reactant side. Any questions on that there? Now, if a change is imposed on the system at equilibrium, we will get some shifting to occur. And I think actually we're going to lay it up there for now. It's a good stopping spot since we're getting to the end. All right, we will lay it up for now. We'll continue in a bit.